In this video, we're going to review the general mechanism for bromination of alkenes. This reaction is an electrophilic addition reaction to the double bond, and bromine or the electrophile adds across the double bond. So let's look at this simple reaction right here. The first step for any reaction mechanism is to determine the nucleophile and the electrophile. The double bond or pi bond is going to be our nucleophile as it is electron rich. Bromine has a low energy empty orbital, so this is going to be our electrophile. So in chemical reactions, nucleophiles always attack the electrophile. So the first step would be something like this. We're breaking that bond right here. Now, based on similar reactions that you might have seen, you might think that the intermediate should be a carbocation, so something like this. However, in reality, that's not the case, as we're going to discuss, so this is not the intermediate. The reaction actually goes through a three-membered bromonium ion. So let me just draw that. Then we have bromide ion. And this is our intermediate bromonium ion. Okay, so now let's just look at the curly arrows that we drew. So this indicates that we're making one or forming one CBr bond, and we're breaking that BR-BR bond. But if you look at the intermediate, we actually have two CBr bonds right here. So another way to better show the reaction mechanism is actually like this. So the pi bond is going to attack here, and then this bromine acts as both as the nucleophile and the electrophile. So the lone pairs are going to be nucleophilic, and they're going to attack one of these carbons and make the second carbon-carbon or carbon-Br bond, and we're going to break that. So now we're forming two CBr bonds. You could think of it this way. So you're forming a carbocation, and then the positive charge is being stabilized through the lone pairs of bromine. However, I just want to emphasize that this is not the real reaction in this case. So that's not what's happening. This is just for you to maybe understand this a little bit better. Okay, so now that we have our intermediate, the bromonium ion, it's positively charged, so it's going to be the electrophile, and we have bromide ion floating around in the solution. That's going to be the nucleophile. So the nucleophile is going to attack. We're going to break that bond. Now this step is an SN2 step, meaning that the addition of the nucleophile is going to be opposite of where the leaving group is going to leave, and inversion of stereocenter is going to happen if there's a stereocenter, as we're going to see. So that means that this reaction happens, or this addition is actually anti-addition. And this is the product that we're going to get. So we have two BRs opposite of each other. So this is one reason that the reaction can't be going through a carbocation intermediate, because if it was, then the anti-addition would not have been possible. So this is a stereoselective reaction. Selective because only the anti-product is going to form. We won't see any syn on product. Okay, so before moving on, we had bromide ion as the nucleophile, but if you do the reaction in methanol, so in solvents such as methanol or water, then the nucleophile in the second step is actually the oxygen in methanol oxygen in methanol or water. And it's not going to be the bromide ion. Okay, so in this case, or in this example, it didn't really matter where bromide ion attacks. So it could either attack carbon number 1 or it could attack carbon number 2. We get the same product either way. But what if we have an intermediate like this? So maybe carbon number 1 or carbon number 2. Then which one, where bromide ion is going to attack, 1 or 2? Well, remember we said that this step is actually an SN2 step, so meaning that the bond formation happens at the same time that the bond is being broken. However, in real life, not all substitutions are pure SN2 or pure SN1, and that's one of the cases right here. So we might start losing or breaking the CBr bond right here, and that gives us the intermediate one shown here. So this CBr bond is being broken and we put a positive charge right here. Or we could break this one instead, and that gives us intermediate number 2. So again, this CBr bond is being broken and we put a positive charge on this carbon. Now, based on what you know, just take a couple of seconds. Which one of these intermediates do you think is more stable? 1 or 2? So 1 is going to be more stable because this is actually a tertiary carbocation, and we know more substituents we have on the carbocation, the more stable it's going to be. This is only a primary one, so that's not the most stable one. So that tells us that this is the bond that's being broken, and meaning that the bromide ion is going to attack carbon number 1, because when this bond is being broken, it's going to be more stabilized compared to intermediate 2. So this is important, especially if, as I said, if you do the reaction in water or methanol, because in those cases you have oxygen as the nucleophile. So here the oxygen attacks this carbon, the more substituent one, and the oxygen of methanol again attacks this carbon here, so the more substituent one. So that's why these reactions, we say these are regioselective, as the bond formation in the second step only happens for a specific carbon. So in this case, the more substituent carbon. Okay, so bromination reaction can also produce stereoisomers. So if you look at this cyclohexene, and if we add bromine to it, we get this intermediate right here. So this is our bromonium, and bromide ion can then attack one of these carbon. Again, in this case, it doesn't matter which carbon it attacks. And we said that this is an SN2 step, so we're going to see inversion of stereocenter. So I'm just going to highlight so you can see that we got inversion of stereocenter. So we get this stereoisomer, and we can get the other enantiomer as well. So I'm going to put plus minus, and we get the other enantiomer if we form this intermediate instead. Okay. Another diastereomer possible is this one here, but we will not get this one again because of that inversion of stereocenter in the second step or the SN2 step. So this is not formed. So be very careful when you draw the products for bromination of alkenes. Okay, lastly, the reaction is also said to be stereospecific, and that's that just means that the geometry of the starting alkene determines which stereoisomer is going to be formed. If you look at the example here, we have Z alkene and E alkene. So if we do bromination, for Z alkene, we get 2 stereoisomers shown here. Instead, if we do the E alkene, we get this one here. I just want to emphasize that this is a meso compound because we have a plane of symmetry. And that's why these reactions are stereospecific. So I highly encourage you to convince yourself that these are the product just by going through the mechanism and what we just discussed so far. So you can make sure that these are actually the products. Okay, so let's review quickly. We talked about bromination of alkenes. It goes through a brominium ion as the intermediate. This is a 3-membered ring. The second step is addition of a nucleophile. It can be there either bromide ion, or if we do reaction in methanol or water, it's going to be the oxygen in methanol or water, and this happens in SN2 step, which means that this is an anti-addition and the reaction is stereoselective. The reaction is also regioselective, meaning that the second step, the attack for the second step happens at the more substituent carbon, because the positive charge formed can be more stabilized. And lastly, we said that the reaction is also stereospecific. So depending on if you start with Z or E alkene, you're going to get different stereoisomers. Thank you for watching.